Okay, I'm going to close attendance. So you have another class with me today at 5:30 p.m. Yes, everyone?
Okay, sir.
All right. Okay. So our topic today will be on binary tree lah. Okay. So what is binary tree? So basically, it's arranging a data in a tree structure, but it's according to a hierarchy. Okay. So I think you've already covered this in your discrete mathematics. All right. Okay. So inside the tree, there are elements that we call nodes. So when you implement this node, you're basically going to have a data and have a pointer, right? But the way you design this node, right, must reflect a tree hierarchy lah. Remember here, tree got left subtree and right subtree. So when you create a node using for a tree, right, for your implementation later on, you need to put in a place whereby you can keep the data and the pointer. Because one pointer will point to the right, the other pointer will point to the left. All right. Can you guys see my screen?
Yes, boleh.
Yes, can
Okay.
see.
Okay. So the top of a node of a tree is called a root. Each node has a parent except for the root. Okay. Each node can have 0 or more children. A leaf is a node that have no left or right children. Two nodes that share the same parents are siblings. And internal nodes are nodes with at least one child. Okay. So here are basically the nodes. This is the root. Okay. This line connecting these two nodes are what we call as edges as well. Yeah. All right. So in total there are 70 nodes here. All right. The root will be electronic RS. The children of RS will be R&D, sales, purchasing, manufacturing. R&D and sales are siblings. All right. Leaf node are nodes that don't have any children, such as R&D, purchasing, what else? Domestic. All right. Internal nodes are electronic RS, sales, manufacturing. Okay. So it has to have at least one child. That is not a leaf, yeah? Okay, so what is a path? So path basically is a traversal of the node lah. So it's a sequence of nodes that's connected together. A simple path is a path with no repeated nodes. So it goes one way only. All right. A path length is the number of vertices connecting the sequence of nodes in the path. All right. So you see for the path, international, overseas, and Africa and Australia. So this path, the length is 3. Okay, because why? 1, the vertices is this node here. 1, 2, 3. Okay. Any questions?
No, sir.
Okay. Okay, no questions. All right. Okay. So this is a structure of a node. Sorry, a tree. Okay. This is the root. Okay. Here is what we call as the height of the tree. So height 1, height 2, height 3. But it's called. But the height is the number of nodes in the longest path. Okay. But the hierarchy, this is what we call as depth 0, depth 1, and depth 2. But the height is 3. Because height 1, height 2, height 3. Hierarchy is depth 0, depth 1, and depth 2. Okay. This line connecting these two nodes. Okay, nodes are also known as vertices, yeah? Nodes are also known as vertices. So, the connection, this line here is what we call as edges. Okay. So, V and W are what we call as adjacent to one another. Okay. This and these are what we call adjacent. There's a connection between these two nodes. All right. So if you look at this example, A is adjacent to B and B because there's a connection. All right. Now, incident is where there is an edge between these two nodes. All right. So, E here is incident on V, is also incident on W. Okay. And we can also say B is incident on E and W is incident on E. All right. So, two are considered as adjacent when they have lines connecting them together. But for this one, it's called incident because V is incident on E, and W is incident on E as well. Okay. Any questions for this one? For this slide? Okay, a degree of a vertex is basically the number of edges incident on that vertex. Okay, so here V, what is the degree? So number of edges incident. So how many edges are there? 1 and 2. So these two are incident on V, so the edges is 2. Any questions?
No, sir.
Okay, so far this is all theoretical, yeah? So what are the properties of a binary tree? At most, okay, every node we have 2 children at most. Alright, so left 3, right 3, so at most 2 lah. Alright, so it will be each child node is labeled as a left child or right child. Alright, now left subtree and right subtree are themselves binary trees. Okay, so this is an example of a binary tree. So this is the root. B here is a parent of B and E. B and E are what we call as a sibling. B is the left child of B. G is the right child of C. Alright. This left subchild by itself is also, this subtree by itself is also a binary tree. Alright, with F as its root. Okay, so you have def 0, def 1, def 2, and def 3. So these are other examples of binary tree, or binary tree with 1 node, binary tree with 2 nodes, binary tree with 2 nodes and 3 nodes. Right? So what is a full versus a complete binary tree? Alright? A binary tree is full if each node is either a leaf or has exactly 2 children. So this is a leaf. It has exactly 2 children. See? 2 children, 2 children, a leaf. Okay? So a binary tree is complete if all levels except possibly the last level are completely full. And the last level has all its nodes on the left side. So here is an example of a complete binary tree. Okay. Now it's not complete yet because you have to include this one here to make it. Oh, sorry, this is complete but it's not full. Okay, to make it full you have to put in this node here. All right. So you see all levels, okay, have node on the left side. So have node on the left side, node on the left side. Okay. So how do you calculate the nodes? All right, the maximum number of nodes. All right. So basically, there's a formula for that lah. All right. So you can calculate the number of nodes. All right, at a level. Okay. You can calculate the maximum number of nodes and the maximum number of leaves using a formula. All right. So here is a node at level 0. So the height is 0. Okay. So at that height, the number of nodes is 2. Okay, here you replace by 0 height. Okay. So it will be at level. So 2, 0 here. It will mean it's at level H here, which is 1. Okay. Now, to find the maximum number of nodes, it is using the formula 2h plus 1 minus 1. Alright, so you replace the h value and then you get the maximum number of nodes. Alright. So maximum number of leaves is also based on the formula 2h. Alright, so which is 2 to the power of 0. So you get 1 here. So now, if it's level 1, height is 1, maximum number of nodes at level h will be 2, 1. So you get 2. Okay, so it's here level 1, so maximum number of nodes is 2. To find the maximum number of nodes, we use the formula 2, 1 plus 1 minus 1 is equivalent to 3. So it's based on this formula here. So here you see 1, 2, 3 nodes. Okay, for the whole binary tree. So this is 1 for the whole binary trees. Maximum number of leaf for this one will be 2 as well. Okay. Now at level 2, so at height 2, number of nodes at level 2 here, maximum will be 4. So maximum of list also 4 lah. Alright, but maximum number of nodes will be using the formula 2h plus 1 minus 1. So you end up with 7. Any questions?
No, sir.
No, sir.
So here's how you represent a binary tree in an array. So is there a formula for this one? There is a formula as well for this one, yeah? But for now, you see, A, index 0. You always start with the left, you see. B, 1, then C. Then D, E, followed by F, G, and then H, and then I. But it's actually based on a formula lah, whereby left child is formula 2i plus 1. Right child, the formula is 2i plus 2. Alright? You can also find the parent using the formula I minus 1 divided by 2. This one here. Okay? So for example, B and C is a child of A. Okay? So where do you place B? Okay, so you put inside the formula. The formula is B here is a child of A. So A here will be the parent. Okay, the parent of B is A. So A is at level 0 here. Okay, the I is 0. So 2 times 0 is 0 plus 1. So B is at index 1. Okay, so the right child is following the formula 2i plus 2. So what do? You replace 2 by 0. So 2 times 0, 0 plus 2. So it's at index 2. So you get C as 2 here. Okay. So what is D's parent? So D here. D is at index 3. So you put inside the formula here. 3 minus 1 is basically 2 divided by 2. So the parent of D here, okay, will reside at index 1, which is D here. So you see from the tree, it's also B. Okay, so you can try the formula, okay, and then you will basically get this array. So an array must grow and shrink as items are inserted and deleted into the tree. So a good choice if a binary tree is not complete or almost complete. Okay, so at most every node has 2 children. So what does this mean? A good choice if the binary tree is not complete or almost complete means is basically linked list can be used to represent binary tree that is not complete or almost complete. All right. So every node has at most 2 children. Okay. So you need to have a place whereby you keep the data. So since every node must have 2 children, so if this is a node, so it must point to left and right. So it will have 2 pointers, which is L link and R link. So L link is left link, R link is right link. Alright, so L link will point to the left subtree, R link will point to the right subtree. So this is an example. So it's actually like a direct translation of the nodes here. So node A here, 2 pointers left and right. Left points to the node B. So now here B here, you see got children at D. So right points to node D, but the left pointer must point to null. Same with D, its right pointer must point to null because it has no right child. Okay. Whereas the left side pointer will point to the node G. So how would you define the struct? So struct, name of the tree, the data, 2 types of pointer, 1 point to the left, 1 point to the right. The element type depends. If you're pointing to integer, it'll be integer. Of integer type, right? If it's right, then it points to integer right. Okay. Okay, but it should it's all basically a binary tree node lah. So basically the element type is it's a mix of, should be integer. Yeah. So here will be integer. If a character, here will be a char. All right. So any questions regarding how to create the struct? Struct,
No question.
name of a node. Okay. The info here will be the data lah. So data is integer, so here will be integer lah. Right. So binary tree node. okay, it will be a type of a node, this node here, but it points to another node. So the type will be binary tree node. Okay, the data kept inside it depends. If a char is a char, if it's a character, it's a character. Okay. A pointer to the root. Okay, the root is pointer is outside the binary tree. Alright, so pointer, the root will be outside, the root will be identified by a pointer for root. Okay, it's not outside the binary tree. So what are the typical operations that you can perform on binary tree? You can check if the binary tree is empty. You can search inside the binary tree. Okay, you can insert the data inside the binary tree. You can delete an item from the binary tree. You can find the height. You can find the number of nodes and list inside the binary tree, copy the binary tree, and traverse the binary tree. So when you traverse a binary tree, there's three types: in order, pre-order, or post-order traversal. So to insert, delete, or look up for any values inside the tree, you need to traverse it, meaning you have to go through the tree. Alright? So the traversal must start at the root. Okay, so the key here, it must always start from the top here. Okay, but the order got three types, which is in order, pre-order, or post-order. Okay. So whatever it is, you have to visit the node first, and then you decide to visit which subtree. Alright. So three types of traversing: in order, pre-order, or post-order. So basically, the order how it travels is basically a repetition of root to its left subtree or its right subtree. So there's three different orders here. So but every time you execute one type of traversal, right? So whenever it reaches the next node, it will perform the same type of traversal, the same sequence. So that's why it's recursive. So in order, you visit the left. So here root, visit left. So here become root, you visit left. So here become root, so you visit left. Nothing here left, then you go to the root. So you get D. Then you get G, because it's right. So this is considered as a left subtree. Then you go to the root back, then you get B. Then you go to the right, then you get E. So this is the left subtree. Go to the root A, so you get A. Then you go to the right, but right here, C got children. So this becomes the root. So you go left, nothing. Then you go root, C. Okay. Then you go F. F here got child. Okay. So here become another root. Okay. So he go left. Alright. So this one becomes a new root. Left, nothing. Root, H. Right, nothing. So left, then root, F. Then right, nothing. So you get this order. Okay. Next is what we call as an in-order traversal. So in-order traversal, it's still in-order traversal, okay, but this is the implementation. So it says that as long as the pointer haven't reached null, you're going to go to the, first of all, you go to the left subtree. Okay. And then you get the info, then you go to the right subtree. So traverse left, visit node, traverse the right subtree. Now that is in order. So for pre-order, it is root, left, and right. So go here, root is A. And then go left. Left here got B here got children, so it becomes the new root, so B. Alright? And then go to the next node, which is D. D no children but got G here. So it becomes the root itself. So get D. So root, left, nothing. Then you go to right. Right? Here got no children, so you get G as the root. Alright? So here finish already. The left subtree. Next you go to the right, which is E. So finish this one already. Okay? And you go to the right subtree. Now right subtree here got children. So root becomes C. Left, nothing. Right, you get F. Okay. So you have the C here. Okay. Root, left, right? F got children, no? F H, so it becomes a new root. Okay, so you have F, then you have left H. Okay, you got no children. Okay, so it becomes a root, so you get H. So for pre-order, as long as they haven't reached null, okay, because you see, you go to the root first, so you print out the data first, then you visit left, then you visit the left subtree, then you visit the right, then you visit the right subtree. So get value in node, left subtree, right subtree. Okay. Now for post order. So for post order, you have to traverse the left subtree first, then you go to the right, then you go root. So from A, okay, you remember left, right, root. So A, left, B. B got children, B. B no children, okay, so left, right, so you got G. Okay, because here got no children, so you take G, and then you get the root B. So left, right, E, so you get E. Then root B, so you get B. So left, right, you get C. Okay, but you see, now C here, C got children. So left, right. Okay, so here C got children. Okay, so you go to the left. No, now children, left, right, root. So you get H first. Then you get here left, right, nothing. So you get the root F. Left, nothing. Right, you have. Then you get the root C. Left, right. Then you finally get A, the root. So the sequence is traverse the left, root, right, and then finally the root. So as a summary, this would be the order of visit. Okay. Now, let's look how to draw a binary tree. Okay, based on the sequence. All right. Did they give the binary tree here? Okay, so this is the binary tree lah. All right. So if you were to do it in order, so what is in order? So in order would be left, root, right. Okay, so it would be left, so it becomes a new root, left, so left, okay, nothing, so left, root, C, then you go to the right. Okay, so here got children, so you get left, E, so you get this E, root, E, and then right, so you get F. So you get C, E, D, F. So here left, root, E, B, right, root, nothing. So here become left, then you go to the root A, then you go to the right. So here got children, left. So here no children, so left, root, H, so you get this H, and then you go right, so you get I. But then I here got children, so you go left, so you get J, I, and then K. So here will become your left, root, J, G, right. But here got children, so left will be M, root, and right. Okay, so this is the in order. So for pre-order, it is root, left, right. So root, left, right. So A, B, C, root, left, and then right. So you get B. D here will be root, left, right. So you get E, E, F. So here, root, left, right. So nothing. Okay. And then you go to the, so here finish already, because here already A. So the root, this finish already, left. So you go to the right. So right got children, so it becomes a new root. Okay, so you get G. Alright. So you go left. So go left, got children some more. So the next root will become H. So you get H. root, left, and then you go right. I got children, so you get E, I first, then J, K. So finish this root, finish this left, so you go right. So here, L, we got children, so L becomes a new root, so you get L. Root, left, M, and no children for the right. So you get up till M. Okay? Any questions?
So far can follow.
Follow, yeah? Okay. So, a binary search tree is a special kind of binary search tree, alright? It's also known as an ordered binary tree. So, data in each node, okay, is larger than data in the left field, but smaller than the right. Okay? So, is this a binary tree or not? So, a binary search tree, okay, is a special kind of binary tree. It is also known as a binary tree, ordered binary tree, whereby data in each node, okay, it is larger than the left but smaller than the right. So is this a binary tree, a search binary tree? Venorika?
I think yes.
Why is it? Because you see, the definition is data in each node is larger than the data in the left field. So if you look here, this one here, okay, is it larger than, so it's larger than the left because there's nothing, but is it smaller than the right?
Oh,
Is it smaller?
no.
No. So it's not a binary search tree. Alright, 78. Is it smaller than 60? No, it's bigger, right? So this one is not a binary search tree. This is what I call as any tree, any type of tree. So arbitrary binary tree. It's considered binary tree, got left subchild, got right subchild, but it's arbitrary. But so it's just basically any type of binary tree. So this is a binary search tree. Because you see, 60 is bigger than 50, but smaller than 70. Okay. 30 is smaller than 50, but 50 is bigger than 50 is bigger than 30, but smaller than 58. And all this number, you see, is all on the left side is smaller than 60. But all the number on the right subtree is bigger than 60. So it's a binary search tree. Okay, Venorika?
Yes, okay.
Okay. So Venorika, which one of these is not a binary search tree?
C.
C?
Is it?
Okay. C? Oh, okay. What? C or what? Cannot hear lah, Veronica. Can you speak louder, please?
I think it's C.
You think it's C? Okay. Can I know why? Which of the following is not? It's not a binary search tree. Yeah. Sorry. Which of the following is not a binary search tree?
Because for C,
Mm-hmm.
the 5 is larger than the left child, which is 4. And then on the
Yeah.
right child, there is nothing there. So no. Yeah. It's nothing there. So it should be the right child should be the data should be smaller than the right child. Since there's nothing there, so I think it's not a binary search tree.
Okay. All right. Any other ideas? Everyone else? Any other answer? Can we have who else? Yeah. Faris? Faris, he all looks like a binary search tree. Okay, never mind. Carrie? Erin Chong.
Yes.
Okay. Which one is not a binary search tree in your opinion?
I think all can be binary
Huh?
search tree. I think all can be.
All can be. Wow. Okay, all. Okay, so if you see a binary search tree, right, it's an ordered binary tree. Meaning if I want to search the number 28, right, if I go here, I search, okay, is this 28 is in the left or right? So 28 is smaller than 78, so it should be on the left side lah. Alright, I know it's never gonna be on the, sorry, this I should use this example. If I want to search the value 28, so it has to be on the left side here because it's less than 60. Alright, so if I want to search for 28, so if we go less than 50, less than 30, so it should be on the left area. Okay, but if it's the value, say, let me see from this one, 59. I know 59 also, it will also go down here. You will not go here because to go 59 here, it must always be bigger. Alright. So here, fulfill the condition, 2 is smaller than 3, 3 is bigger than 4. So any number at this left subtree is still smaller than 5. Okay. 7 bigger than 5 lah. Okay. Same with this one. 2, 3 smaller than 5. 6 and 7 is bigger than 5. 6 is also bigger than 5. So anything bigger than 5 you go to this tree. Here Venorika. So here actually Venorika, it says basically there is nothing lah. So you cannot say there is not a binary search tree. Okay, because basically it's trying to say any number bigger than 5 should belong to the right subtree. So does it fulfill this condition? Data in each node is larger than its left child, smaller than the right child. If you look at it, it is small. 4 is smaller than 5. 3 is smaller than 4. 2 is smaller than 3. Okay. And if you want to search maybe a number 1, if you get number 1, right, you definitely know it will be put in this area here, left subtree. Okay. It won't put here. Now, for the value here, 1 will also definitely be here on the left subtree. Because 1 is smaller than 5. Okay. It is smaller than 4. It's smaller than 3. So it will belong in this left subtree. Now, E. 1 is smaller than 5. Okay. Smaller than 4. Smaller than 3. So it belongs in the left subtree. Now, if you were to put 6. Now, 6, is it bigger than 5 or not, Venorika?
Yes.
Okay. So it belongs on the left subtree or the right subtree? Six is bigger than 5. So data in each node must be smaller than its right child. Okay. So data in each node larger than its left child but smaller than its right child. So if the data is 6, it belongs on the left or right? Venorika, you there?
Right side?
Right side. So it belongs on the right side. So this becomes a new node, correct? So 6 belongs on the left or the right?
Sorry sir, I'm starting to get a bit confused.
Okay, tak apa. Okay, you ada nombor 6 kan? Untuk dia jadi binary search tree, for this to be a binary search tree, okay, this number must be bigger than the left subchild and, must be bigger than the left subchild but smaller than right subchild. So if you were to insert the number 6, okay, you want to insert number 6 in this tree, this is an ordered tree. So 6 is bigger than 5, so it goes to the right subtree. Now 7, this is 7. So 6 will be on the left subtree or the right tree here. It will be left child or right child if you have the number 6. So if this is a node, 6 must be smaller than 7 because smaller node, the left subchart is smaller number, the right subchart is the bigger number. Alright? Don't look at this one first, Rita. Don't look at this one first.
Okay.
Okay. So is this a binary search tree?
Oh no, it's not.
No, it's not a binary search tree. Because if you put 6, then you see the 6 actually belongs on the right subtree. It has to fulfill this condition. So 6 should be this area here, not this area on the left. Okay. So the order is, if it's smaller, then you go to the left. If it's bigger, it goes to the right. Is that clear, Veronica?
Yeah, it's clear now.
Okay. So typical binary search tree operation is to search inside the binary tree, to insert data, to delete that data inside the binary search tree, find the height. So this one I think we cover inside you punya lab. Find the number of nodes in the binary search tree, find the number of lists, traverse the binary search tree, and copy the binary search tree. So if you want to search an item in binary search tree, this is the algorithm. If the root is null means there's nothing to be searched. Else, you're going to have a pointer, alright, that points to whatever the root is pointing to. Now, as long as current is not null and not found, so you haven't found the item yet, if current info is the same as the search item, set on to true. Else, if current info is greater than the search item, okay, so current points to that particular node. If it's greater than the search item, okay, then follow, go to the left subtree or follow the left link of the current. Else, go to the right side. So because you see the condition here, if smaller than 5, then go to the left subtree if you want to search. If it's bigger than 5, you go to the right subtree. So that's why this one doesn't work, because 6 here is supposed to be smaller than 5. Okay, because when it travels the node, it goes to the root first. Then go here, then go here. Alright? So to find the minimum element in the tree, traverse from the root, okay, to the left recursively until you reach the null value. Alright? This one will be the smallest one. Whereas to find the maximum, traverse from root to right recursively until the right is null. Alright? So the maximum value or the minimum value, for the minimum value will be, since you traverse to the left side, it will be the node whose left node is null here. Right, so we traverse left recursively until find a node whose left node is null. Okay, maximum value, you're going to traverse the right subtree until the right node is null. So this will be the maximum, this will be the minimum. Because why? When you traverse recursively to the left, dia punya anak here will be null. Alright, for maximum, the right side will be, the right child will be null. So 80 will be the maximum value. Okay, so this is the insert implementation for binary search tree. So you can refer inside your textbook, page 621. Okay, but new version have a new value lah, new page number. So create a new node. So you have to create a new node first. Okay, and then insert the data. All right, and then set the L link to the and the right link to null because it's a new node. Okay, you haven't inserted first. You just create the node, you put the data, set L link and right link to null. Okay. Now, if the root is null, all right, then the tree is empty. So the root will point to this particular new node that you have created because the tree is empty. But if the tree is not empty, then you're going to have a pointer that points to whatever the root is pointing to. Okay. As long as you haven't reached null, okay, you're going to have a pointer called trail current that points to whatever current is pointing to. Okay. If current info is the same as insert item, so the data that you want to put is basically the same with the whatever current info is pointing to. Because this is ordered list, you cannot have a duplicate. Okay, it's an ordered list, so you cannot have a duplicate. So you tell the user cannot insert because it's a duplicate. If current info, okay, is the bigger than the insert item that you want to insert, all right, then you go to the left subtree. Because remember, the node, the left subchar must be smaller than the node, and the right subchar must be bigger. So if it's smaller than the current info value is bigger than your item that you want to insert, that means it belongs in the left subtree. Else, go to the right subtree. Now, when you want to add in the node inside the binary tree, if trail current info, okay, is bigger than insert item that you want to insert, okay, then make the new node the left child of the trail current. Okay, so if it's smaller, then you make it the left child. Else, you make it the right child. So, you can apply this logic when you want to draw this binary tree. So, 45, you have a new node 25. 25 smaller than 45. So, you go to the left. 15. Go to 45, smaller than 25. So, it belongs here, 15. And 30, 10. Smaller, smaller, smaller. Now, here, 6 is smaller than 15, so it belongs on the left subchar. 20, smaller than 45, smaller but bigger than 15, so it becomes the right char. Okay. So, so basically different sequence of these elements will generate different trees. Now, if you want to delete an element inside the binary search tree, all right, if it's just a leaf, you can just delete it. All right. If the node to be deleted has no left child, but it has a right child, then you replace that node with the right child. If the node that you want to be delete has no right child, but it has left subchild, then you replace it with the left child. But what happens if it has to be deleted? If the node you want to delete have both children, left and right, this one is a bit longer. So this one is an example. Have left subchild, so you just delete it. It's a leaf, so you just delete it, no child. Case 2 here, yes, right subchild. So you just replace the node that you want to delete with the right child. So you get 50, then you get 35. Here the node you want to delete, it is the right child. So you just the node you want to delete is this 80 here, but it has a left child. So you just delete the node, you replace it with the left child. So you get like this. Okay. But if it has two left and right child, for example, the value, which one I want to delete here? Okay, 5. Okay. So if 5 here, you still need to keep the property of binary search tree, whereby the node is bigger than the left child, but the node is bigger than the left child, but smaller than the right child. Okay. So how would you do it? So you got to rearrange back, whereby. So here, the binary search tree says it wants to. Oh, sorry. This one is that it wants to have this element into a binary search tree. All right. So here, 5, 21 is bigger than 5. 19 is still bigger than 5, but smaller than 21. 25 is bigger than 21. Still keep the property of a binary search tree. So this one, 19 as the root. 5 smaller than 19, 21 bigger than 19, 25 bigger than 19. All the values here bigger than the root, smaller than the root. Okay, or the node, yeah. So still a binary search tree. So what happens for this example? You want to delete the value 1 here. Okay, you want to delete the value 1. So if you want to delete the value 1, you have to, this new subtree here must fulfill the concept, okay, of a binary search tree. Okay, so if you were to delete here, so you get 0, 5, 4, 3. Okay, now if you were to put 2 here, okay, you replace it with 2, would it fulfill the properties or not? So you check 0 smaller than 2, and 5 here would be bigger than 2. Okay, so the first solution would be to replace the node to be deleted by the minimum element of the right subtree. Okay, so left subtree is 0, so minimum element would be 2. So you just replace 2 at the node that you want to delete. That's solution 1. Another solution here is to replace the node to be deleted by the maximum element from its left subtree. So just now we were looking at right subtree, now we look at the left subtree, so maximum is 48. So we just put 48 here. Okay, so but then you must always check whether it fulfills the binary search tree properties. So 33, 30 is smaller than 48, 53 and 57 bigger than 48. So 32 smaller than 35, 35 is bigger than 40, and 45 is bigger than 40. So it still preserves the binary search tree properties. Okay? Any questions?
No,
So this is the
far,
type.
no question.
Got a question, is it?
So far, no question.
No question, yeah? Okay, alright. So this is the time complexity of the binary search tree. Alright? So average case is all O log n. Worst case scenario is On. Okay? But for traversal, it's all the same because you have to go through all the nodes. Alright? So it's On. Alright? Worst case scenario for search, insert, delete is that you have to travel through all the nodes lah. Else you're going to find the item immediately. Alright? Not immediately lah. Somewhere before you search all the nodes. Is there any question? Hello?
Excuse me, sir.
Yes?
Can you hear me? I am Wong.
Yes?
I have a questions about the project. That one.
Okay, later. I want to ask a
Okay.
question regarding the lecture first.
Okay, thank you, sir.
Okay. Any questions for the lecture?
So far, no lecture question.
Okay, and if no questions, now this evening you got lab at 5:30. Okay. So regarding the projects, please ask me during the lab. Okay, so it's because it's going to be combined 2 groups. So I think it's better that if you ask a question regarding in the lab, then the question can be shared with the other group as well. Okay? Hello? Is that okay with you?
Okay.
Okay, all right. So I see you at lab today at 5:30. So the lab is not much. It's just one question understanding. So you have another extra question, only one question extra, okay? So I'll see you guys during lab, yeah? 5:30 today.
Okay, sir.
Thank you, everyone.
Yes, sir.
Bye-bye.
Thank you, sir.